Hello, everybody. I'm going to be going through section 3.9 in this lecture. So 3.9, let me get my whiteboard shared. Okay. 3.9 is a section called differentials. And I will first explain the idea about differentials to you, and then we will do some problems. There's 4 different types of problems in this section, and we'll go through each of those. The first thing we're going to be talking about is what are called tangent line approximations. And tangent line approximations, guess what? We're going to be using the derivative. The same thing we've done with all the different sections in chapter 3. Don't forget that the derivative f prime of x gives us the slope of the tangent line at a value of x, and let's say x equals c. That also gives us the slope of the curve at that exact point too. But remember, we can also find the equation of the tangent line. Once we have the slope and the point, we can find the equation. So if I have a curve with the tangent line, and that point is x, I take that back, let's use c. That point is c f of c. Then the equation of the tangent line, we'll take the derivative. We're going to evaluate it at c, and that's f prime of c, and that equals our slope. So I have my slope, I have my point, and I can find the equation. Y minus y1 is m times x minus x1. So that would be y minus f of c equals f prime of c, which is my slope, times x minus c, using the y value from our point and the x value from our point, the same that we would with any equation we're trying to find. And then the tangent line approximation is taking this, adding this to both sides. And so this is what we call the tangent line approximation. That is y is equal to f of c plus the derivative at c times x minus c. It's essentially the equation of the tangent line, and we use it to approximate things, which is what we're going to be doing next. Okay, let's move on to the next. Here's the type of problem, the first type of problem. Basically, the tangent line approximation is a linear approximation because the tangent line is a line, a linear function, and it's a linear approximation of the function at x equals c, or of y at x equals c. So again, we've got this y equals f of c plus f prime of c times x minus c. So here's the problem. Find the tangent line approximation of f of x at, well, let's get the function first, equals 6 over x squared at this point. And remember, when we work with derivatives, because we're working with slope, from the very first day of class, I've been telling you we have to talk about where. And we're talking about where, we're talking about at this point. This is our function. First thing we're going to need to do is take that in this form and write it as 6x to the minus 2 so that I can more easily find the derivative. And that's going to be negative 12 x to the minus 3, which is negative 12 over x cubed. That's our f prime of x. So we have to evaluate that f prime of 2 at the particular c value that we're talking about. And so that's going to be negative 12 over negative 8, which is I take that back. That's negative 12 over positive 8. And that's 3/2 if I simplify that, negative 3/2. So we have our f prime of 2, which is going to go here. We have our f of c, which is the 3/2 that came with our original point. We have our value of c, which is 2. So our tangent line approximation would be 3/2. That's f of c, or f of 2. Negative 3/2, and I'll write it that way. You could put the minus here instead, times x minus 2. And if I want to simplify that by taking this, it's going to be positive 6/2, and then you've got 3/2 here. So I can rewrite that into a better form, a simplified form, 9/2 minus 3/2 x. So that's our tangent line approximation. And what we do with this is that we're going to do a couple exercises with this. We use a table, and we're going to show how well this does approximate. And there wasn't room for the table here, so that's why I wrote that kind of big, and we're going to switch over now to do a table. Okay, so we have this tangent line approximation, 9/2 minus 3/2 x. We're going to make a table, and we're going to have f of x, which is the actual value of the function at the x value, and then we're going to have the approximation. So this is the actual, and this is the tangent line approximation. And this f of x, remember, was 6 over x squared. And we're going to look at that. We're talking about the point x equals 2. And we're going to do another table similar to what we did with limits. We're going to look at, to the right of 2, coming from the right, we'll look at 2.01. We won't get quite as close. And then 2.1 and 3. Coming from the left, we'll look at 1.99. That is pretty close. We'll also look at 1.9, and we'll look at 1. So these are values that are getting close to 2. We're not going quite as extremely close as we did when we were talking about a limit. We know that the value here is 3/2. That was given to us as the point 2 3/2. So that's your x and your y for the actual function. And at the exact point, remember, the tangent line at the exact point actually will have the exact same value of y as the function. So this is also 3/2, and you could confirm that by plugging it into this 9/2 minus 3/2 times 2, you're going to end up with 3/2. 9/2 minus 6/2 is 3/2. But these other values you'd get from plugging them into your calculator. 6 over 1 squared is 6. 6 over 1.9 squared is 1.66. 6 over 1.99 squared is 1.52. And this is 1.5, by the way. 3/2 is 1.5. This is 0.67, and this is 1.36, and this is 1.49. The 3/2 here, if I started to look at the approximation, these are the actual values in this line, the actual value of the function, the y value there. If I start to look at the approximation, I'm going to get, if I plug 1 into this function, I'm going to get 1.65. I take that back, I get 3. This is 1.65. This is 1.52. This is 0. This is 1.35. And this is 1.49. Now, in both cases, whether I'm looking at the actual here or the approximation, my y values are getting closer to the actual value at 2, which is 1 1/2, 3/2, 1.5. But you'll see that if I'm away from the point quite a bit, look at the actual value versus the approximation. The approximation doesn't do any good when we're that far away. Look at this. I get 3 for the approximation and for the actual value. But once I get closer, when I'm only 0.1 away or 0.01 away, look at how close these are to each other. And that's what we're trying to show with a table like this, is how well this tangent line approximation estimates the actual value. Now, at this point, what you're thinking to yourself is, if I can find the actual value, why not just find the actual value? The approximation takes me just as much time, and I'm not saving any time by using the approximation. But you'll see as we go forward with some of these other types of questions having to do with differentials, that the approximation can actually save a lot of time. And really what I'm doing with these first few examples is just kind of proving to you that it's true. So that's the only table I'm going to do. Another thing to remember, actually, I should point out, is that this is the tangent line approximation at this point. And as I get close to this point from either side, at this value of x or c, x equals 2. I'm going to have a completely different line if I move somewhere else on the curve. So this is one of those things we've done before where it only applies right there at that exact point. And visually on this little sketch I have here, the tangent line, you can see it's not very close the further away we get, but it's very close when I'm right there near the point. And we're going to talk more specifically about that coming up next. Okay, so clearing this off. Here's what's happening with a differential. And this is theoretical. It's not specifically steps you would take to solve a problem. I'm going to try and draw a better graph. I have a pretty nice graph in my notes, and there's one in your book that you could use. Yeah, I don't like that. I'm going to try and erase just that line that I just drew, the tangent line. Okay, let's try and make that be a little bit better. No, I don't want to erase anymore. I want to finish drawing. Darn it. Okay, that's a little better. Okay, so let's set this up. Here's C. If I am some distance away from C, I move delta x in this direction, then my tangent line is no longer right there by the curve the way it is here. So let's label a few things. This is the point C, f of C. This y value here, that's f of C, that distance. And this distance here is delta x. The distance here is going to be f prime of c, the first derivative evaluated at c, times delta x. And I'm about to explain how I know that or why that's true. This distance right in here from the line where f of c starts up to our curve, that distance is delta y. And that's important. This is the change that happened in y when I moved delta x. Okay? I was already y value of f of c, and then when I changed delta x, when I increased my x value, I added delta x to c, then my y value went up by this much, delta y. So that's an important thing to understand. This point up here is c plus delta x, that's my x value, and then my value, of course, is f of that. So that's the picture I want you to keep in mind. This equation, the equation of this tangent line we just learned, we're going to use this form of that equation. And that relates to this right here. The y value, if I'm at this point, c plus delta x, the y value there is going to be f of c, which is this amount right here, plus this, f prime of c times x minus c. And I'm going to explain that in a few minutes. Okay, so this is the actual change in y based on moving delta x along the x-axis here. And I want to explain this. How do I know that that's this amount? If you say that the slope at c, the derivative evaluated at c, is the change in y divided by the change in x, and then I multiply both sides by delta x, then these cancel, and so I can say that the change in y equals f prime of c times delta x, and that's what's happening here. I'm for the tangent line, not for the curve, but for the tangent line. You see the tangent line goes from here to here when I go from here to here. So this distance is going to be the y over the x, that's and that would be the slope of the line. And so the change in y, this change in y is actually equal to this. This is like a little side note for why that's equal to this. Or you could just take it as given that that's equal to that. Look what happens. Think of a limit idea as delta x smaller and smaller. So as I shift this way, delta x gets smaller and smaller. This this tangent line approximation, the value here is going to get closer and closer to the actual. So this change in y here and this f prime of c delta x, those get closer and closer together as I get like down here. You know, here's the value for this f prime of c delta x, and then there's the value for delta y, and they're pretty much alike. They're pretty much the same. So what we say is, as we get close to c, so as delta x gets smaller and smaller and smaller, then we talk about delta y being approximately equal to f prime of c delta x. Now we're going to take this over to the next page and talk about that, because this is where we get to the actual idea of a differential. Okay, so delta y is approximately equal to the derivative of the function evaluated at c times delta x. And if you want to think of it this way, this side is the actual change, and this side is the approximated change. This is called the differential of x, and this is called the differential of y. Differential, look at the first part of the word, difference, something changing. The change in y is approximately equal to the change in x times the derivative of the function evaluated at whatever c value you're talking about. And change in y we have been calling dy, change in x we've been calling dx, and so I'm going to make this a little more general. Instead of at a particular value of c, this is a general way that we would talk about differentials. And this is the definition of the differential of y. It's to take the derivative of the function times dx. Some people like to think of differentials as coming from this, and this is not a bad way to remember it. We know that the derivative of y with respect to x, dy dx, is equal to f prime of x. Just multiply both sides by dx. They would cancel here. And in differential form, if you will, it looks this. So this is one type of question you're going to be asked, is just to find the differential for the function. And what you're going to do is take the derivative and then say dx right after it. So what I want to do next is a couple more examples. This will be the second type of problem that you need to be able to do with differentials. And this is another kind of problem where we're kind of proving to you that it's true. So let's look at those next. Basically, we're going to compare dy and delta y. So we did that in a table. We compared the actual change in y and the approximate change in y using the tangent line approximation. Now we're going to do it with some problems that I'll show you the way that we do these. They're not in a table form, but let me clear the page because I need a whole page for one of these. Okay, so here's our function. This is what you'll be given. And x is -2, that's our c. And delta x is 0.1, that's given to you. That's our dx. I'm going to need my derivative, y prime, which is my f prime of x, and that's going to be -4x. That's a pretty simple derivative there. And we're going to find the change in y, which is the actual change, and then we're going to find dy, which is the approximated change. And what's happening here, if x is -2 and delta x is 0.1, then I'm going to go from, I'm going to be going from -2, and then -2 plus 0.1 is -1.9. So along my curve, so on the curve, going from -2, and we'll find that number, to this point, -1.9. Imagine you're going along the curve and you're at -2, and then your delta x is 0.1. So I add 0.1, and now I'm at -1.9. If you take -2 and you plug it into your original function, you're going to have 6 minus 2 times 4. So you're going to have the point of -2, -2, -2. And if I take negative 1.9 and I square that, multiply it by 2, subtract that from 6, I'm going to get negative 1.22. So you're not given all of that information. You're given the function, you're given the x value, and you're given the delta x. So from that, you have to actually construct the fact that you're going from this point to this point. Now, what's the actual change in y? The change in y is the y value that I ended up at minus the original y value. And that's equal to 0.78. So as I moved along the curve from this point to that point, y actually changed by 0.78. My approximation, my differential would be the derivative times dx. So dy would be negative 4x, which is what I found up above, the derivative, times 0.1, that's dx is our delta x that was given, and that's going to be negative 4 times negative 2, my x value, times 0.1, and that's going to be positive 0.8, and that's the approximation. Now, it's pretty close, 0.78, 0.8. If I were going to use the differential approximation, this is the short and sweet version of what I would have to do. I take the derivative, I multiply it by dx. This was given, the dx. This only took me a few seconds, and I'd be done. If I were going to use the approximation, I don't need to find these 2 points, which is what took me all the time, and then finding the actual, subtracting the y values after I found them. So the differential approach can be very fast. 0.1 is a fairly small change in x, which means that if you're going along the curve, your tangent line is going to be a pretty good approximation because you're pretty close to the actual point where x is negative 2. Let's do one more of these. I'm going to clear off the page and we'll do one more of these. Okay, here's my function. Y equals x to the 4th plus 1, x equals minus 1, delta x equals 0.01. Again, this is our dx. Let's do the approximation first, just so you can see how fast it is. Approximate dy is equal to f prime of x dx. Take the derivative times dx. The derivative is 4x cubed dx. 4 times negative 1 cubed times 0.01. That ends up being negative 0.04. I'm done. I have the approximate value of dy. Let's look at the actual. To do that, I'm moving along the curve from negative 1, some y value I have to find, to negative 1, and I move plus 0.01. I'm at negative 0.99. And this value, if I plug in negative 1 to my original function, negative 1 to the 4th plus 1, and then I've got to do negative 0.99 to the 4th plus 1. The point that I get here is negative 1, 2, and then this is 1.961. And so the change in y, the actual change in y, is where I end up minus where I started from, and that's going to be negative 0.0394. So this is the actual, delta y, and this is the approximation. And you can see that they're quite close to each other. They are less than 0.001 apart. And this one took me far less time. The differential approximation took me far less time. So those are, the first type of problem was tables, using a tangent line approximation to complete a table and see, as I got closer and closer to x, how the tangent line approximation was quite close to the actual change in y. Actually, I take that back. For the table, it's showing you how close the tangent line approximation is to the actual y. With the differentials here, we were talking about showing how the change in y, the actual change in y, could be approximated by using the idea of the differential. The next type of problem is actually it's sort of a subset of what we were just doing. And that is just you're asked to find the differential dy of a given function. And to do that, we're basically going to use the idea that dy equals the derivative times dx. That's this is just where and then you're not actually using a specific point and using it. You're just finding the differential. So let's look at a basic function first. And my derivative, and then I'll wait to put the x at the end. And by the way, don't forget to do that. We have a constant multiple 3, and then 2/3 x to the minus 1/3 when I take the derivative, dx. I will count off if you forget to write dx at the end. This will be 2, the 3's cancel. I would end up with 2 over x to the 1/2 dx. That's my answer. That's all you're being asked to do in this type of problem, is find that. I think I have room for one more here because it's not very long. If my function is a trig function, dy is going to be the derivative. The derivative of the cosecant, remember, is negative cosecant cotangent. So it's going to be negative cosecant 2x cotangent 2x times the derivative of the inside function. And then don't forget your dx. Remember, this is a chain rule. You've got the outside function, then the inside function. So dy is negative 2. We'll pull the 2 down. Cosecant 2x cotangent 2x dx. And that is the answer to that one. It's just as simple as that. It's actually what we did as part of the earlier, longer problem. Okay, let's do one where we're using the product rule. So if y is x tangent of x, this is the part of the test where you're going to be showing me you still remember how to do derivatives. You're going to have to use the product rule for this. So my derivative, and remember, some of you guys like to write y prime instead of dy dx. You can no longer do that when you're doing differentials, because you need dy here and then dx is going to be on the other side of the equation. So you can't write the derivative as just y prime. We're going to have the first times the derivative of the second, which is secant squared, plus the second times the derivative of the first, which is 1. And you really need to do this. You really need to put that whole thing in parentheses and then dx to have it be a proper form. Okay, so that's your answer to that one. And then let's do one where we have to use the quotient rule, just to remind you guys about that. And this one I'm not going to continue with until I rewrite it. I can't emphasize enough how important it is to do that, to remind yourself that for the derivative of that numerator, we are going to need the chain rule because it's the derivative of something squared. So I'm going to use the quotient rule in general, but then when I'm taking the derivative of the upper part of the numerator, I'm going to have to use the chain rule because that's an outside function of something squared and then an inside function of secant. So dy is going to be the denominator times the derivative of the numerator minus the numerator. You can go ahead and write it back this way for that, times the derivative of the denominator. So I'm going to write that right away because that's fast and easy, the derivative of the denominator. The numerator or the denominator of the entire thing is that squared. Don't forget that part. The derivative of secant x squared. First, you're going to have 2 times secant of x to the first power, because that's the derivative of something squared, 2 times that to the first power. Then you're going to have the derivative of secant, which is sectangent. Now, I wrote that a little too big, so I kind of blocked myself out of room. But do you see I have secant squared here and here? So I could actually pull that to the front. And don't forget your dx. If you don't write it on interim steps as you write it in your final answer, I'm going to be okay with that. But it's a good idea to keep writing it so you don't forget it. So I have secant squared x as a common factor. I'll pull out to the front. And I'd be left with the tangent of x. Actually, you know what? I have a 2 in each one too, don't I? So I'll bring out 2 secant squared x. I'm going to be left with tangent of x here times x squared plus 1. And then I'm going to have minus x from this right here that I didn't pull forward. All over x squared plus 1 squared. Okay, there's one more example in my notes I'll let you guys look at if you want to pull it out. That's one that's a product rule. And last but not least, we're going to get to our last type of problem for this section. And these are called propagated error problems. Let me explain what we mean by that. We're going to be able to use our differential to figure out, to approximate a change in y. And what we're going to do is use that to estimate errors that are propagated when you measure something, physically measure something, and you're off by a little bit. So let's say here's an example. The radius of a ball bearing, the little metal balls, and you have them of different sizes. So let's say you're talking about one that has a radius of 0.7 inches, but it's often given this way. This is an error. And that's because when a factory is manufacturing ball bearings, they aren't all 100% exactly alike. There's a small amount of error. And depending on what you're manufacturing, your error can be larger or smaller. If you're manufacturing something that goes in like a replacement hip, a hip replacement, then you're going to want to be very exact, and your error allowed is going to be very small. If you're manufacturing rods, a rebar to go in concrete, your error can be bigger because that's not as it's not as critical that it be exactly the same. So you're typically given something that has an error involved, and then if I use this measurement in a formula, in a different formula, then what happens is that I propagate the error, and I end up being off by even a little bit more. So if I'm using this radius in, for example, another equation like volume or area, then you would be propagating this error because you're squaring the radius, or you're cubing the radius, and so therefore you're cubing the error or squaring the error. So let's look at these. Often tend to be sort of geometric in nature, and let's look at what's happening here. So with an example, I think it'd be clear then. So the radius of a spherical balloon is measured as 8 inches with a possible error of 0.02 inches. And here's the problem. Write out the problem here, then we'll go to the next page to work it. The way it's asked is use differentials to approximate the possible propagated error when computing volume of the sphere. And then there's always, or almost always, a second part. Find the percent error. So here's how big the error could be, and here's what percent it is of the volume. So let's go to the next page to actually work out this problem. Okay, the volume of a sphere is 4/3 pi r cubed. I would give that if I asked you about volume of a sphere. This is a 3. We need to find dV. What we're doing here is we're using dV to approximate delta V, which is the actual change in volume. And this would be as it inflates. Okay? And this is going to be, first we find the derivative. And that's going to be actually differential. We find the differential, which is essentially the derivative. The is going to be 4/3 pi times 3r squared dr. And so when I work that out, that's going to be, the 3's cancel. So I end up with 4 pi r squared dr. And when, from the words of the problem on the page before this, what we're talking about is when r is 8 and dr is plus or minus 2. I'm sorry, 0.02. That was given to us in the example. This is our error, our possible error in R, and what we're doing is using that then to talk about what does that mean in terms of what does that make our possible error in V be, in volume be. So what I'm going to get is 4 pi times 8 squared times 0.02. We just use the positive version of that, and we end up with 16.08. So that would mean plus or minus 16.08 square inches. I'm sorry, cubic inches, because we're talking about volume. And that would be our propagated error. That would be part A, finding that. And then I said there's a part B, and that is what percent error is 16.08? Because 16.8 sounds kind of big compared to the 0.02 that we had for our error, our possible error in the radius. Suddenly in the volume, we have this giant propagated error of 16.8. But if I look at the volume, I'm going to need what is the volume when R is 8. And that's going to be 4/3 pi times 8 cubed. That is going to be 804.25. And then I take 16.08 and divide that by 804.25, and I find out that that's only 0.005. Oh, I am sorry. I just switched examples. Oh, good grief. Let me do this. I'm looking through my notes and I jumped. Okay, forget about this right here. This is good up to here, and let's switch pages to find the percent error. Okay, so the volume being 4/3 pi r cubed. If r is 8, then the volume is 2144.66 cubic inches. And now the dV, which is our propagated error, we found that to be plus or minus 16.08. And the question is it really, that seems big compared to the 0.02, but is it really big? And we look at 16.08 divided by 2144.66, and that is 0.0075, and that is 0.75% error. So that's actually fairly small, right? What this tells us, this volume here, is that the volume is at x equals 8. The volume is 2144.66 plus or minus 16.08 inches cubed, based on the fact that the radius itself had a possibility of error. That means there's a possibility of this much error in the volume. And again, it seems like a lot, but it's only 0.75%. So we'll do one more example of this type of problem, and that's the last type of problem, propagated error problems. The next example I think I'll do is, let's do a rectangular solid, actually a square. Not even a square solid, a cube. Let's call it a cube. Okay, and look at a 3D version. Again, a little messy. I'm getting better with this drawing board, but we have a side when it's a cube. The volume is cubic, so side cubed. And the side is 15 inches plus or minus 0.03. So that's the error in the side. We would call that ds. I would take the volume formula, and dV is going to be 3s squared ds. And that would be telling me the possible error in volume due to or propagated from the possible error in side length. So this is going to be 3 times 15 squared times 0.03, and that ends up being the 20.25, and that would be plus or minus when we talk about 20.25 inches cubed, since we're talking about volume again. What percent is that? And the volume is 15 cubed, which is 3375 at this point where the side is 15 inches. So 20.25 divided by 3375 is 0.006. So that's 0.6% error that we've got in our volume. Again, yeah, this seems like a lot, this 20 inches, the possible error of 20 cubic inches, I should say, but it's only 0.6% of the volume at that point. So it's actually quite small. So that finishes up my lecture on these. I do have some practice problems that you could do. There's one more in the notes about surface area of the sphere. And then there's additional problems in the homework in the book. And I need to look and see if any of those match the WebAssign problems I assigned, but I assigned several problems in WebAssign for doing this as well. We will talk about this Monday and Wednesday to the extent that you guys want to. I'm going to stop the recording now, and I will see you in quote unquote class.